Thank you for inviting me. This is probably going to be a bit of a change of pace here. I'm a systems researcher, but we do actually pay attention to algorithm design because it's actually very important to us in the field of real-time computing. So what I'm going to do is to try to give you a rundown of some of the major issues in real-time system design, especially those bearing on the algorithmic issues. So, but let me just start my presentation with an observation. Actually, one of the most important things that I observe in my career in this area is that probably the most difficult part in my job, okay, is really the first bullet, is the requirements capture. Okay, because a lot of actually bad designs actually come from misunderstanding of what the users want. Okay, so I'm going to use one example to illustrate that, and also actually you want to use this example as a vehicle for explaining the notation that I'm going to use for the rest of the talk. So, so let me so let's say that a customer who comes in and says that, okay, well, I need to reset and resynchronize the system clock on an hourly basis. All right. So, but what does he mean by that? So there are at least three interpretations I can come up with, and in fact, all three interpretations can make sense under different circumstances. Okay, the first interpretation says that basically, okay, you got to resynchronize the clock on the hour at 7 o'clock, 8 o'clock, and so on and so forth. Okay, right. And the second interpretation says that, oh, what I really want you to do is to do a resynchronization of the clock between 8 o'clock and 9 o'clock, and no, do it between 9 o'clock and 10 o'clock, and do it between 10 o'clock and 11 o'clock. I don't care when exactly you do it, but you do it, okay, according to that schedule. And the third interpretation says that, well, I don't know when you do it, okay, right? But if you do resynchronization, then you better do the next one within the hour. Okay, so it's like the minimum separation between two synchronization attempts should be no more than an hour. Okay, so why is this important? So in fact, okay, there was an accident, no, it was a near accident that was reported in the news in LA. So you don't have to read all of these. Basically, what happens is this. Okay, right? So the requirement basically says that they need to resynchronize the clock on an hourly basis. All right. So the interpretation that the operator selected was that well, I can synchronize the clocks, let's say at 8 o'clock in the morning. All right. But since I'm not required to synchronize the clock on more than on an hourly basis, then I can wait till 10 o'clock, okay, before I do another synchronization. But of course, if you do that at 2 hours, okay, in between the two synchronizations, and that was actually not acceptable. And in fact, that caused a problem that was important in the news because there were some near accidents because of that. So this is the motivation of why I selected to present this talk using a notation that I invented a long time ago. And this notation will be used to explain some of the technical problems so that my community is interested in. So this notation is called real-time logic, RTL for short. Okay, so it's a very simple notation. So the syntax is simply that, okay, you use the first order predicate logic, but you add an uninterpreted function. Okay, let me call it an add function. It takes two arguments, the name of an event, okay, and then a instance index I. Okay, and at EI is simply just the time, okay, the absolute time at which the event happens for the ith time. Okay? All right, so those examples were about my talk and so on and so forth. So technically, actually, the RTL is really a subset of Pressburger arithmetic with an additional uninterpreted functions symbol. Okay. So that is the syntax of this notation. Let me give the semantics. So to give the semantics, I need to define what a computation is, okay, for this logic. So computation is, you think of it simply just as a timetable, okay? So this timetable has columns, okay, one for each event, one for each instance, and one row for each event. So you simply just, for each computation, you just simply fill out the time at which those events happen for various instances, okay? So you can simply, so now you can interpret all the predicates accordingly in an obvious way. Okay, so now I'm going to give you some of the kind of main type of problems that we want to solve. The first type of problem is that, okay, suppose we capture the requirements of a system using this notation, then one problem that we want to solve is to do some analysis on it to make sure that this problem specification is okay. And in fact, usually there are certain safety requirements the system's supposed to obey. All right. So the input is you give a specification in some notation, and this is an English description of that of the requirement, right? And then we're going to translate it into a formal notation using RTL, right? And then what we need to do is to look at, okay, the type of safety queries, okay, that the user wants the system to obey, and then we want to build a black box, okay, and we input the query, input the system specification, and we want to provide an answer. Okay, there are basically three types of answers. One is that the black box may come back and say, yes, you're fine. Okay, your system is safe with respect to this safety property. Or the black box may come back and say, no. There's something inconsistent in your spec. And in fact, if you build this the system, you're bound to run into trouble with this type of safety property. Okay, and but actually, more often than not, okay, that's the third type of answer the black box will give you. Okay, if it gives you any answer at all. And basically, the black box says that, well, it depends. Okay, and in fact, no, basically, your system is kind of underspecified. Okay, and in which case, what I want to do is for our black box to come up with conditions. These are kind of runtime checking that the user must do in order to make sure that the safety the property is not violated. Okay, so this is the example. Okay, so by now you must kind of read what that means. So this is actually a fairly realistic example. It's a typical communication system where you have a sender sending messages to a receiver, and there is a finite buffer. In fact, the buffer has only basically one slot in it. All right, and then you want to make sure that the buffer doesn't get overflow. Okay, so using RTL specification, in fact, okay, this is hopefully it's fairly easy to read. So SAM is the sensor. Okay, so the for example, for the first time the sensor is exercised. Okay, it's for the instance I equal to 0, so it's at time 0. So at S1 is 0, and at S2 is equal to P, and so on and so forth. All right. So what the processor does when it gets the sample of sensor data, okay, is to process it, and in fact it has a window in which to process the data. So the window is defined by basically the up arrow P, okay, which is the start of the processing. So each action that's performed by the sensor, by the processing system, okay, is denoted by two events: the start of the processing and the completion of processing. Up arrow P and down arrow P. Okay. So now you have some inequalities that govern the timing restrictions on when those events can occur. And the safety assertion that we want to ascertain, okay, is the one at the bottom. Basically says that, okay, well, you better finish up the, you better not start the sensor for the first time before you basically start processing the previous sample, assuming that in fact the first action of the processing is to snatch the sample from the sensor. Okay, so the buffer is empty again. Okay, so there are well-known solutions to this problem. Okay, and in fact there are semi-decision procedures that we can use to do this, but they are really not very practical. In fact, this is one of the challenges I would like to pose to everybody. Is that, look, I mean, you know, if you really want people to be able to build black boxes that can answer these type of queries efficiently and quickly, right? And we really need to do more work solving problems of this sort. Okay, but in any case, so this is an example of the analysis that we do, actually semi-automatically. The difficult part here is that actually, in order to solve this type of problem, it's really a satisfiability problem. Okay, we need to be able to basically figure out which inequalities are really relevant, okay, to the problem. And in fact, in this particular case, okay, we actually need to focus on the inequalities on the left-hand side. All right, and if you by magic you know how to do that, okay, right? Then in fact you can actually derive a condition, okay, which is that theta, okay, which is the scale, the time scale between the sensor and the processor. Okay, assuming the two clocks are not accurately synchronized, which is always the case, almost. Okay, in a distributed system. So, so now this shows that if you have a good analysis tool, you can actually help the user to basically to watch out for, okay, what constraints, okay, that might be violated in a run, so that you can warn the user that something might go wrong. Okay. So, and I'm going to basically point out the problems and needs as I go along. Okay, so for analysis problems, okay, there are actually the few problems that we would like to, at least for me, I would certainly like to clear up. Okay, and some of which actually certainly are algorithmic problems. And actually, the first problem I want to point out, okay, is that actually using the RTL actually it's really in some sense it's a cheat, okay, because we would certainly be able to say that, okay, for the same event E, okay, let's say that you take a sample of a sensor, right? So the I plus first sample should certainly happen no early than the I the sample, okay, right? So it's at EI plus 1, it should be actually strictly bigger than at EI. So that makes practical sense. All right. But notice that, okay, in fact, we do not preclude that an event might never happen. So in fact, if somebody never decides during a run of the system, never uses the sensor, right? So the add function term will be undefined. Right? So now, an easy fix is that, well, if it never happens, we can pretend that, okay, in fact, it happens at time infinity. All right. But then you have to deal with nasty the technicalities, like, okay, well, you mean to tell me that infinity is bigger than infinity plus 1, right? According to that. Okay, right. So these are technicalities that we have to deal with, and in fact, there's a way to deal with it, although I don't really like the approach at all. And basically, instead of using an uninterpreted function, we can use an uninterpreted predicate, okay? And that actually kind of sidesteps this problem. But that only sidesteps the problem because, okay, because we actually, by doing that, we actually make the specification a lot more cumbersome, okay, in the sense that whatever you want to say about the behavior system, okay, if an event happens, right, then something should hold. But almost in all this assertion that you have to make, that you want to make, you have to kind of prefix it with the assertion that, well, if something happens, okay, then this is true. All right. And I would certainly like to see work, okay, that the theory community might be able to help us to kind of make this less cumbersome, and yet it has to have a sound foundation, obviously. Right. Okay, so in order to do the analysis, we have to look at the decidability of theories of this sort. RTL is undecidable because actually it's pretty easy to show that with an uninterpreted function symbol, you can actually encode squaring, okay, by which you can actually encode multiplication, right? And that basically says that the theory is undecidable in general. However, okay, those proofs, okay, are artificial in the sense that, okay, it involves basically timing of events which are really not realistic at all. So for example, if you allow using the squaring function to describe the time at which event happens. So the first event happens at time 1, say event happens at time 2, and then the third one is time at 4, and then 9, and so on and so forth. So it gets spread out in time. And that's really not, I mean, no real system actually behaves like that. Okay, right? Actually, there are really useful fragments of this logic, okay, and in fact, dealing with real-time system specification in general, such that you can solve the decidability problem, and it's actually, as a result of that, you can also do synthesis, okay, which is actually it's a large part of the work in our community, which is to study how to allocate resources, especially CPU, in order to meet the timing constraints, okay. But all these problems are hard. Okay, so even for very simple ones. Certainly, any practical tools and any good algorithm that you guys can help us to design to solve the resource scheduling problem would be very useful to us. So let me give you an idea of what a synthesis problem looks like. So basically, what we want to do is to synthesize a scheduler, okay, that will take a set of specifications, like the one I just presented, and then automatically turn out a scheduling algorithm for meeting those timing constraints. Okay, so technically, what we want to do is really to construct a model, okay, such that we can actually use the model as a timetable, right, to drive the computation at runtime. So actually, we have built tools to do this sort of thing. Okay, in fact, the Boeing 777 was the avionic, the speed was built by Honeywell, and in fact, we've been, well, actually when they were doing that, we were talking to them, and we had a lot of exchange of ideas about how to do this sort of thing. So this is actually a very practical problem. So the 777 actually has quite a number of tasks that it has to run. Okay, so the number to look at is really the bottom. Okay, if you want to count the number of constraints, okay, and constraints in the form of, okay, some event happens before or within another event happening with some time offset. Okay, so they're about, in this particular case, about 8,000. However, okay, the difficult part with this problem is that this is not a big contract. Okay, in fact, no, this is it's usually, okay, you can kind of express it in terms of the conjunctive normal form. So there are a lot of disjuncts in that specification. Okay, so you can think of it this way. Okay, so for each disjunct, you have to basically solve a set of inequality on the order of about 10,000. Okay, inequalities, right? So if you have, let's say, 1,000 disjuncts, okay, right? Then you basically have to solve 2 to the power 1,000 set of inequalities, even though each set of inequalities actually is fairly easy to solve because they're in some particular form. Okay, but anyway, okay, there are techniques that we can use to solve this type of problem. So let me just skip this, okay? And basically, the result is that we can use a solution to generate what is known as a cyclic executive, okay, in the avionics industry. Okay, and the idea here is that you pre-build a static schedule which you repeat when you're running the system, kind of over and over and over again. Right. Now there's some technicality that we need to take care of, okay, which is that actually the constraints, some of them are fairly complicated. Okay, so you got to kind of break it down, and then the way you break it down actually is determined by how you interpret those inequalities. And in fact, I remember that this was done almost 20 years ago. So in fact, when we first looked at those specifications, we misinterpreted some of those constraints. And as a result of that, we could never get a solution until we got back to them and say, what do you exactly mean by this? Okay, then realized that, yes, in fact, the reason why we did not get a solution is because we didn't get the interpretation right. Okay. Also, there are some other issues, okay, that we need to worry about. Okay, so the first one is that if you build a model for this set of predicates, and in fact, the model is really an infinite size table. Okay, right. So because you don't know how long the system is going to run. So in general, right. So certainly we do not have memory, infinite memory to store this table. So basically, you have to somehow come up with a finite representation of this table, which can be done actually for a large subset of these type of problems, okay, that actually people have to deal with in practice. All right. There are also what we call external events. Okay, these are the events that happen anytime, like the pilot pushing a button. You don't know when it's going to happen, but if it happens, then something else must also happen within a certain time. All right. So how do you use actually a finite table to to basically drive the system to respond to those events, and if you do not know when those events will actually happen at runtime? And let me just say that in fact the techniques that you can use to solve that, okay, but by no means have we solved the entire problem. Now what is challenging for tomorrow, okay, is that the FAA, okay, is very much set on basically using static schedules, okay, for the avionics system that we built. Okay, maybe they're changing their minds, okay, but the last time I talked to the people who kind of know about what they do, I was told that in fact they still prefer using basically this kind of table-driven type of schedule. And there's a reason for it, because it's very easy for them to be able to certify an avionics scheduler, okay, by looking at these tables. All right. But what if I want to build systems which are a lot more dynamic in nature in the future? Okay. So in that case, all right, so I do not have only one set of specification, but in fact the specifications might change depending on the mode of operation the system is in. Right? And that will make the problem a lot more difficult. And actually, no, I think the cyber physical systems, okay, that NSF actually is it has been kind of embarking on, actually has this type of characteristics. Okay, so okay, so let me just again, okay, emphasize that yes, in fact, we can solve the problem, but we need no better techniques. So for example, I would certainly like to see techniques which are not based on model construction. Okay, so maybe there are other techniques that can derive scheduler directly from the logic specification itself. I have no idea how to do it, okay, but I hope that somebody can do it. Also, as we push the frontier of real-time systems, okay, we're going to, at some point, I think we have to kind of abandon using static scheduler and use dynamic schedulers. For which, actually, there's a whole literature of results starting from, in fact, the Apollo project. In fact, there's a seminal paper written by Liu and Leyland in 1973, in the journal ACM, in which they established basically kind of two main results, and they show that the earliest deadline first scheduler is optimal, okay, and in fact it can use this, it can use the processor to its full utilization. They also introduced the concept of schedulability analysis, okay, which is basically a sufficient condition for a set of periodic tasks to be schedulable. All right. Now, since then, okay, it's been basically like a cottage industry that's kind of grown up around this sort of thing, and depending on what type of application that you want to do. So the user paradigm is that you look at application domain and say, okay, here is the scheduling task model, okay, that you can use to describe this, right? So instead of using this logic description and say, hey, think of it as a combinatorial optimization problem, okay. But usually it's kind of infinite horizon type of optimization problem, okay. And there are different kind of flavors of it. And I don't have time to go over all of that, okay. However, okay, one of the weakness, okay, of the current approach, okay, which actually may be somehow connected to the previous talk about robustness, okay, or how fragile a system can be, okay, which is that it turns out that if you use a non-preemptive scheduler, okay, all the famous results, okay, in the Liu Leyland paper, for example, are based on preemptive schedulers, where a task which has a high priority than another task can always preempt a low priority task at any time it wants. Okay. However, okay, if you restrict the amount of preemption that you can do, okay, then the problem becomes interesting because actually the schedulers that are built with non-preemption, okay, turn out to be non-robust. So what is robustness? So here's a very simple example. So I have 3 tasks. Okay, right? So the first task has 3 units of completion time, and actually it's recurring, it's periodic. So every 3 time units, okay, it comes back with a request. So the up arrow is a request. So T1 has a request at time 0, and then time 5, and so on and so forth. And T2 is the second low priority task. Okay, it has a period equal to the 15. Okay, and then but it has second priority, and therefore after T1 finishes, so T2 can use the CPU, and T3 has the lowest priority. This is a schedule for this set of 3 periodic tasks. But notice that, okay, if I actually decrease the execution time of the T2 by a little bit, right, and therefore I allow, okay, T1, okay, to start, okay, a bit earlier, and in fact it will cause a deadline miss, okay, in T2. All right, and this is simply because it's a timing and the anomaly, okay, that people have observed, and in fact this is a very well-known phenomenon, and in fact it was a paper by Maneker, okay, that back in the 60s, okay, they talk about multiprocessor timing anomalies. Okay, it turns out that in fact for real-time computing where deadlines are concerned, this anomaly actually happens even for uniprocessor systems. And in fact, the problem is pretty bad, okay, because, okay, the problem cannot be diagnosed just by testing alone, all right? In fact, this example, okay, then you don't worry about details, but what it shows is the following. So I give you a set of tasks, okay, and they're scheduled by a non-preemptive scheduler, all right? So now you have a schedule. However, if I decrease, okay, the execution time of a task T2 by a little bit, you still get a good schedule. But if I keep decreasing it by a little bit, okay, all of a sudden, okay, you start missing deadlines. Now notice that actually we are decreasing, not increasing, the execution time of the task. All right? Okay? So, and what is worse is that actually you can keep on doing this. If you decrease it even a bit more, now the task becomes schedulable again. If you decrease it a little bit more, it becomes unschedulable. A little bit more, it becomes schedulable, unschedulable, schedulable, so on and so forth. Okay? So, if I'm a testing engineer, how am I going to test this? Okay. So the moral story is that here is again the challenge to you is that, okay, look, I mean, we really need to have better technology to design robust schedulers, okay, that allow limited preemption. All right? And in fact, okay, this actually is a more complicated issue because in order to solve these type of problems, we really need to work with the computer architects who now start using multi-core. Multi-core is actually a nightmare, okay, because the cache behavior, okay, affects the timing analysis by a whole lot, okay, and kept running out of time. So, okay, actually, this is really interesting problem that I really want to spend time on. Okay, so let me just mention it. All right. So this is the next wave, okay, for real-time system design, which is open systems. Okay, open system, okay, is has the characteristic, okay, that you are not allowed to know what the application timing requirements are. So I give you a set of applications. Okay, let's say 5 of them, right? Each one of them has its own timing specification. You are allowed to use the same set of resources to try to execute these 5 set of tasks with different timing specification. But you're not allowed to look inside, okay, what the specification are. So actually, so in this case, is it possible at law to come up with a resource allocation scheme so that you can meet all the timing constraints, okay, without looking at inside? Well, you can kind of do that, okay, by basically using infinite time slicing. So the idea is that if I look at, okay, a resource that is CPU, let's say that I can slice up the execution time infinitely often, all right? So basically for each time unit, I give a fraction of the CPU to each partition, okay? A partition is the basically the set of processes that perform, okay, a particular application task. All right. But if I do that, then in fact, in theory, I can solve this problem. So I can have a scheduler, okay, which do not have to know about the internal requirements of each application, and yet, okay, I'll be able to meet all the timing requirements. But of course, this is not practical because, okay, infinite time slicing, okay, is not a practical technique to use in practice. All right. So how do we solve this problem? Well, basically we have to use limited partition, and in fact we introduce this notion called real-time virtual resource. And basically the idea simply is that you can think of your CPU as a computing device, okay, which does not keep perfect time. Okay, it jitters a little bit. All right. However, for some applications, okay, the jitter allowance can be very big. So let's say you're reading email, you don't care about the jitter, as long as it's like within a few seconds. All right. But if you are doing navigation, okay, right, you might want to be very careful about it. So anyway, my time is up, and in fact, maybe over a cup of coffee or drink or something, I'll talk to you about, okay, ultimate real-time research problem. Okay, so I guess I should stop and allow people to ask questions. Yes?
So, as somebody who works on efficient algorithms, I tend to veer away from undecided problems. That's not to be a priority there. I know that in standard model checking, there's been work looking at algorithms for finding finite size counterexamples in sort of model checking and saying, you know, just out and we'll quickly find a small counterexample if there is one.
Yeah.
Is there something analogous that can be done with these real-time systems?
Okay. We need to talk about. I suspect that they maybe. I suspect they're applicable. So basically, what we want to prove